get started, welcome to session 102. I'm Bill Fischofer from the Linaro networking group, and this is the ODP project update. What I'd like to do today is cover several topics, and again, feel free to keep this interactive. If there are questions, let's feel free to ask. Just like to give an overview of the project status of ODP and its status. Review some of the key developments since Hong Kong, since a lot has happened in the intervening 6 months. Talk a little bit about the plans for the rest of this year and as we move into next year. Talk about a little bit about the relationship between ODP and the OPNFV project, which is an initiative that that many may be familiar with, and how that really relates to the concept of what ODP application design looks like, so the emerging model for that. And then finish off by just doing a quick overview, a preview of some of the other LNG sessions and demos that you'll see here this week. So the first question is, what is OpenDataPlane? And this is one of these questions that keeps getting asked, and we've evolved this over the couple of years that the project has been in its existence. And the reason why this is interesting is because there really is a threefold answer to this question. First of all, ODP is an abstract API specification. That's first and foremost what it is. But behind that is also a series of multiple independent implementations of the ODP APIs. So one of the core concepts behind ODP is separation of this API specification from its implementations. ODP, unlike some other platforms, does not have a preferred implementation. It just simply says enumerates a list of functions. And then finally, the third component of ODP is a validation test suite. And so we can go through what each of those are and represent. The ODP API specification, as I said, is an abstract specification that is open source, open contribution, and BSD3 licensed. It is specifically designed to be vendor and platform neutral. It is first and foremost application centric. That is, it covers the functional needs of data plane applications. And it ensures portability by specifying the functional behavior of ODP across any implementation of it. It's defined jointly and openly by application writers and platform developers. And it is architected to be implementable on a wide range of different networking platforms. It's also sponsored, governed, and maintained by the Linaro networking group, which is its organizing group and upstream. Implementations of the API are pretty much open to anyone. So anyone is free to write an implementation of the ODP API from its specifications. And the reason we support multiple implementations is that one size really does not fit all. There is a hugely wide difference in the capabilities and internals, particularly in the range of networking SOCs out there. And so it's very difficult to try to say that a single code base can adequately cover the entire market or every platform that might implement that. So by supporting multiple implementations, we address that. As I said, anyone can create an ODP implementation tailored to their platform. And one of the other benefits of this model is that the distribution and maintenance of each implementation is at whatever its owner wishes. So in particular, implementations can be open or closed source as business needs determine. And you can have their own release and release cycles and service streams associated with them. So you're not, in order to get a fix into one particular platform, you don't have to worry about upstreaming just the implementation details. And the idea here is to allow hardware and software innovation in how ODP APIs are implemented on each platform. Well, by itself, that would not be very interesting because it really wouldn't provide much guidance for, well, how do I get started with this? So in order to assist with the implementing of ODP on various platforms, LNG distributes and maintains a number of reference implementations of ODP. These are themselves open source, open contribution, and BSD3 licensed. And the idea behind the reference implementations is to provide easy bootstrapping of ODP onto new platforms. If you take the most basic reference implementation we have that we call Linux generic, all it requires is a Linux kernel. It's a pure software implementation. If your platform supports Linux, you can take that and be up and running with an ODP implementation on your platform within a couple of hours. And from there, you can then start tailoring it and optimizing it to take advantage of the unique features of that platform. Implementers are, of course, free to borrow or tailor code as needed for their platforms, and they retain full control over the implementation, whether or not it was derived from a reference implementation. And the final piece is the validation test suite, which is synchronized with the ODP API specification level. Again, maintained and distributed by LNG. Also open source, the usual litany. And what the validation suite is really the key to ensuring application portability across ODP, all ODP implementations, because it tests that implementations of ODP conform functionally to the API specification. And this can be run at any time by both users and vendors to validate the implementations of ODP. So if I have an implementation of ODP from vendor X, I can run the validation suite against it and say, yes, indeed, it does in fact match the specification for a given ODP level. Any questions on the components? Okay. So let's talk a little bit about where we are. ODP is about 2 years old now. It was first announced in October of 2013 at LCU 13. Throughout 2014, we had a series of 11 preview releases. And in 2015, we've basically been producing what we're calling pre-production evaluation releases. So we had ODP 1.0 in February, 1.1 in May, July had 1.2, and we just released 1.3 right now. ODP 1.4 and 1.5 are scheduled for later this year, and our end-of-year release, we're codenaming Monarch, which is intended to be the transition into next year, where we really, the theme for 2016 is ODP production releases. And for there, you'll see increasingly a focus on apps and OPNFV, as opposed to just developing the ODP infrastructure and APIs itself. That's not to say there won't be new APIs, but it's just the emphasis is, okay, we want to start really using this and deploying it on a more production basis. So some of the key changes since Hong Kong. In ODP 1.1, we introduced the notion of user metadata support. So packets in particular, this is for packets. So packets have system metadata, things like packet length and what pool it came from, things of that nature. But for many applications, it's useful to be able to tie application-specific data to a particular packet, which is just sort of carried along with that. And so as of 1.1, we have a set of APIs that allow applications to, when they create a packet pool, to specify that, hey, I want so many bytes of user area associated with each packet that can be then managed by the application. In ODP 1.2, we streamlined pool creation by getting rid of some of the extraneous parameters that were there as a legacy. We added default CPU masks and introduced thread masks and thread types. So threads are now come in two flavors, worker and control, with the idea being to have a clear separation from those threads that are designed to process work using the ODP event model, which we'll discuss a little later, and then versus those who are basically providing more supervisory or general processing capabilities for the application. And then in ODP 1.3, which is a fairly major release, we introduced some improvements to packet I/O including the ability to start and stop interfaces, providing some additional parameterization for them, as well as input-output modes. We added parameter structure init routines styled along the what you find in POSIX. So rather than zeroing a parameter area, there's a specific init call to put them into a default state. And we made a number of improvements to the scheduler, including the introduction of scheduler groups and introducing the notion of event prefetching. And then we also finally implemented something which had been on part of ODP from the beginning, which is ordered queues, which we'll talk about, as well as ordered locks. There's been some other changes that are notable since Hong Kong. On the platform side, ODP DPDK launched as a performance platform for x86, which uses DPDK as the underlying SDK for ODP. And the idea here is to enable ODP to support various NICs that have DPDK drivers. So if you have, typically in a lot of SoCs, I/O is handled through integrated I/O adapters. But for general servers and also even for SoCs that support expansion through PCIe, there's a question of how do you access drivers to run those. And DPDK has a reasonable set of drivers already as part of it that enable broad-ranging NIC support. So ODP DPDK is one way of getting access to that. And we have been doing proof of concept work with applications like Open vSwitch using this. And we'll hear more about that later in the week. Also, another open source platform implementation of ODP was announced by Calray, which is not an LNG member company. They're just a company that is interested in ODP and is taking advantage of its open source nature. And they've announced an open source implementation of ODP for their MPPA SoCs. Yes?
So like you mentioned, the new point about supporting, say, PCIe NICs. What is that, say, limited to x86? So the PCIe NICs that you talked about, right, that you could use the pole mode drivers from DPDK.
Right.
Seems like that would be useful for ARM also. So,
yes.
Has there been any kind of evaluation of what it would take to port DPDK to ARM?
That's a good question. The answer is yes. That's under active review. In fact, we know there are lots of private ports of DPDK to various ARM architectures. So one of the interesting work items is to try to get a consolidated public common port for that, and I think that will be something that you'll be seeing more of, later in the year and early into next.
Okay, thanks.
So, but yeah, conceptually, DPDK itself is just an SDK that ODP uses to get access to things like pole mode driver support for NICs. Right now, it's just that if you go to dpdk.org, what you find is code that supports x86. Other changes, there's been quite a bit of significant restructure in the ODP validation suite, courtesy of Christoph. I don't know if he's in the room. Yeah, Christoph, so you can thank him. But this is basically to make the validation suite a lot more platform independent, to really meet the goals that we talked about how it can be separated from any specific platform, so it can serve as truly as a standalone validation of implementations. That's, as I said, that's really to support this separation. In fact, what we're talking about right now is trying to take the existing Git repository and actually split that out so that they can be distributed as separate Git repositories to further emphasize the component structure of ODP. What we're looking ahead to for the rest of this year is ODP 1.4, which is currently targeted for the end of October. The major item on that is a new set of APIs, which is called the Egress Traffic Manager. This is to add QoS support on the output side. sort of mirroring the input classification support that we've had since ODP 1.0. And well, again, I'll be talking more about this a little later. Interprocess communication work, some additional ports, counters, and statistics, some improved test capabilities, and particularly the ability to replay PCAP files, which would provide some additional capabilities for testing DUTs, as well as enhancing the configuration APIs. Right now, if you look at the ODP config.h, it's a series of pound defines, and we want to replace those with API calls, basically. For 1.5, we're looking at what can be done for a generic NIC driver interface. Again, you know, the question of can DPDK be more than just x86. And we're also looking at seeing, you know, what can be done to make better use of RSS capabilities as they relate to the ODP classifier. Since right now, if you look at what RSS is doing, it's doing a limited form of classification on the NIC, which is really just load spreading, but the question is, can you somehow make that tailored based on the classification rules that the application has specified, so that you get a better mapping to, for NIC-based I/O into the classification infrastructure. And then finally, we're hoping to, at the end of this year, transition to what we're calling our Monarch release, where the goal there is to transition to production release cycles and packaging, such as RPM and Debian, and formal use of release candidates. And so again, moving more into now ODP is ready for production use. So let me talk briefly about ODP and OPNFV. For those who are not familiar with it, OPNFV, from their website, they listed their mission as it's a carrier-grade integrated open source platform to accelerate the introduction of new NFV products and services. So effectively what OPNFV is, it's the aims to realize the ETSI NFV vision. So I believe it's about almost 3 years ago now, ETSI launched this initiative called Network Function Virtualization, which basically published an architecture. And the question is, all right, you know, I have an architecture, how do I get an implementation of that architecture? OPNFV is intended to be an implementation of that architecture. And if you look at the various pipe projects that are associated with OPNFV, there's a whole slew of them. But the one that we're most interested is this DPACC project, because that is essentially OPNFV's view of how to do data plane acceleration. And so all these other projects that are in there have to do more with how do you do build systems, how do you do admin systems, you know, implementing all the NFV architecture pieces. So the data plane is really just a small part of this larger ecosystem.
Bill?
Yes?
In the previous slide, you mentioned that OpenNFV is open source thing?
Yeah, in your previous slide, you mentioned that OPNFV, the definition of it said it's open source. Does that mean everything below it is, or that you can have proprietary drivers below it, or what?
That's been something that I think has been discussed in a lot of things. I think their intent is to be as open source as possible. The question of, you know, do you support binary firmware bundles? I mean, Linux makes accommodation for that. OPNFV may well do the same. I'm not familiar with. I think each project would have to, you know, make that determination for itself. If you look at a lot of these projects, they tend to be fairly high level, you know, admin stuff where arguments for proprietary stuff is kind of weak. As you get very close down to hardware, then those arguments become stronger. So if you look at the DPACC project, they basically define two sets of APIs. One which they call a GAPI, which is a general API intended to use by virtual network functions, and then an SAPI, which is a system API representing a platform's native capabilities. And from our perspective, you know, that maps fairly well into the ODP model, where we have a an application API which leverages whatever underlying system SDK or other APIs you have. But of course, DPDK takes a different view, and so right now both ODP and DPDK are essentially proposing themselves as DPACC's GAPI layer. There are discussions that are ongoing between the two groups, so the fact that ODP and DPDK are talking to each other about this. In fact, we just had a meeting this past Friday on that subject. And we're discussing basically how the two projects can cooperate on future architectural direction. But the fundamental issues really surround application design philosophy of what's the approach to building applications with those two products. And so, therefore, I really wanted to talk a little bit about ODP application design. So the real focus of ODP really has three goals. Okay, one is to ensure portability across any implementation of ODP. And again, that's to cover all the diversity that you see in the ARM ecosystem, as well as the ecosystem of other platforms, because ODP is not tied to any specific instruction set. We support right now ARM, x86, MIPS, and Power architectures, as well as, in the case of Calray, they have a proprietary architecture for their processors. So we're really independent of processor architecture. But portability is an important goal. The other is transparent access to platform acceleration and offload. And this is really key, because if you look at the diversity of the ARM ecosystem and the various SoCs that are based on that, one of the things that you'll see is these platforms have very diverse capabilities in terms of what they can do in terms of hardware acceleration. And we'd like to allow applications to be able to exploit those capabilities without the application writer having to be a platform expert for every platform they might run on. This is particularly important in an NFV environment where you may not know what hardware you're going to run on in advance. That's a key attribute. And the final thing is scalability, because one of the things that you're seeing is as we move into a many-core environment, the question is, can applications grow to exploit more and more parallelism in them without needing to do a lot of rewriting? And we also, of course, have to consider migration for existing applications when you're looking at moving an existing application to this new structure. So if we look at how ODP approaches portability, it does this in a couple of ways. First of all, we have this abstract API design, which uses abstract data types such as ODP packet T instead of a platform-specific struct. We also, the selections reflect application use cases, but are balanced against both usability and the ability to implement them efficiently across many platforms. So we're not interested in least common denominator APIs, which really don't provide useful function to applications. But we're also not interested in overly high-level APIs that few, if any, platforms could reasonably implement. So it's a balancing act, which we expect to evolve over time as hardware capabilities become more sophisticated, which they always do, because hardware guys are smart, and they're always having more transistors to play with. So we expect those to evolve. But again, when we define an ODP API, we're looking to ride that line between usefulness and good implementability. For acceleration, we want to exploit the platform-specific acceleration and offload capabilities. As I said, the question is being able to be efficiently mappable directly to hardware platform capabilities. And here I list just a couple of the examples of the sort of things that you typically find in SoCs. Hardware buffer, packet management, integrated I/O adapters, hardware parsing and classification support, scheduling and flow ordering, traffic shaping, all of these capabilities, and many more to come, all of which are part of the innovation that you'll find in many SoCs. And if you were to write directly to a given platform, you would have to then know the intricacies of how those particular functions work for that particular platform, and that's the sort of thing that we try to avoid. So by writing to a single ODP API, you get the benefit of that exploitation without having to master a dozen different platforms. And from a scalability standpoint, we're looking to scale to many core architectures without application redesign. And there are really 5 key areas of ODP that are really oriented around scalability, and we'll talk about these in a little more detail. They are the classifier, events queues, the scheduler, and the new traffic manager, which is coming this year. But the idea is that we really want to be able to enable an application to be written in such a way that the application really doesn't have to be redesigned, whether it's running on 440 or 400 cores. It's just a question of, well, how many worker threads do I create during initialization? So if we look at how packet receive works in ODP, we have a set of Ethernet interfaces which are abstracted into the ODP packet I/O construct. So packet I/O is essentially how ODP represents any sort of an I/O interface. And those feed into the classifier, which is configured through a series of pattern matching rules. The pattern matching rules describe various offsets in packets and fields, what are of interest to the application. And what that results in the classifier putting a packet into a designated class of service based on matching a pattern matching rule. And what a class of service does is it determines the storage pool that packet should belong to, as well as the input queue that it should be put on for input to the scheduler. So that's what a class of service is. It's basically packet storage, where to put it and where to queue it. Okay? And so the idea is we can now take a series of input packets and essentially classify them into flows, which are what is represented by the queues, each of which can potentially be assigned to dedicated areas of storage to ensure that, well, for this class of traffic, I want to be sure that I have a certain amount of storage available for buffering, and so that it's going to get the quality of service that traffic demands. For event scheduling, we now have packets that are on these input queues. Threads call ODP schedule to get their next event. So the scheduler is basically scanning all of the queues and finding the highest priority work that is eligible to be dispatched to a given thread. The thread then gets that. It may invoke various engines, say for instance crypto, to provide services via ODP APIs. The implementations will wrapper whatever underlying hardware capabilities they have so that it interacts with the rest of the ODP infrastructure. So in the case of a crypto, which is doing an asynchronous operation, when that operation completes, a completion event will be scheduled back to the application for eventual processing. In the meantime, the application can go and service some other work while the crypto block is going off doing its processing. And threads, of course, then can call ODP QNQ to add events to queues to be scheduled for further processing. So this is how you basically do a processing pipeline. And so queues are really central to this. So if we look at queues in ODP, they come in 2 types, scheduled and polled. Okay, a polled queue is one which the application is going to take complete control of. It just wants to put things on, and it's going to remove them by making DQ calls directly to it. Useful for some things, mainly more for legacy apps. The other type of queue, which is the more interesting one, is a scheduled queue, and that is basically a queue which is going to be managed by the ODP scheduler. And for those, queues have 3 different types of attributes. They may come in 3 different flavors. And those are the scheduling attributes for the queues. So we have none, atomic, and ordered. So if you have no attribute for that none, it's effectively what we call a parallel queue, which means that anyone can process any event from that queue, and there's no real synchronization between them. atomic queues, events are serialized by the scheduler, which means that only one thread will receive an event from that queue at a time, which means that the application never has to perform any locking. The locking is essentially performed automatically by the scheduler itself. And then the third type, which is in many ways the key to scalability, is ordered queues, which means events can be scheduled in parallel, but order will be preserved. So threads can use ordered queues as well as ordered locks within their processing to handle critical sections within a parallel flow. And we'll illustrate this in the next couple of charts here. So if you have, the classic example here is how do you parallel process a single flow? If I have a flow which requires so much processing that a single core cannot keep pace with it. Say I have a 10 gig flow, and I need to do 2,000 cycles worth of processing per packet, but a given core can only do 500 cycles worth of processing in the time budget that I have. Well, the only way to do that is to use multiple cores on that single flow in order to keep up with line rate. So the idea is the scheduler will dispatch events from ordered queues to eligible worker threads concurrently. So I may have multiple threads that are working on different packets in parallel for the same flow. But the key with an ordered queue is that when they eventually enqueue the results, the fact that they came from an ordered queue means that they will appear on the output queue in the same order that they originated on, independent of the order in which they actually finished by the worker thread. So the worker thread doesn't have to worry about that. That's just handled as part of the infrastructure. So you wind up having this type of worker thread structure where I come in, I'll do some one-time initialization, and now I'll enter a while loop where I call the scheduler to get an event. I now am processing that event in parallel with all other threads that are working on that. If I do need to do some critical section processing that must be done in order, for instance, sequence number assignment, okay, for IPsec processing, we have this concept called an ordered lock, which basically says I need to do a certain critical function in flow order for this section. And that will ensure that that critical section will be entered only in flow order. So packet 1 in that sequence will be executed before packet 2. And essentially, when you're in that critical section, no other thread that's processing concurrently with you will be in the same critical section. I can then exit that, and I'm back doing parallel processing, and then I will enqueue the result and take advantage of the ordering. Yes, Barry?
Do you think that the implementations of ordered lock and unlock would be able to support things like TCP processing, or is that a little bit too large of a chunk of work that?
No, well, I mean, so in the case of TCP, okay, the interesting thing about TCP is you have higher levels of ordering consideration. So this is basically doing packet order preservation. TCP may have a notion that, you know, if a packet arrives out of order, TCP may have to do some manipulation. And yes, the answer is you can use ordered queues for that, but it will require additional application support, because what you're doing is the application will say, this is the order things came in with. Normally, if I did nothing, the order that goes out would be preserved, but I can change that order if I need to. Okay, but it would be under explicit application control in that point. So the final concept I'd like to talk about is the traffic manager. So normally, and this is the way things look before ODP 1.4, is we have a series of threads that are talking directly to packet I/O objects. They just enqueue to packet I/Os, which essentially go to the output Ethernets, or possibly a loopback, which goes back into Ingress. I mean, that's the loopback interface is useful for things like after I've decrypted an IPsec packet, well, I now need to reclassify it because now I can see what was actually in it. But in 1.4, we're introducing this new, we'll call it a black box for the purposes of this discussion, which is the ODP traffic manager. And that itself consists of a series of input queues and output queues. And in between, it's got a series of arbiters and shapers and other things which essentially allow the quality of service metrics to be applied to outgoing traffic so that I can actually shape the traffic to achieve QoS requirements. And there's a series of TM configuration APIs which allow you to essentially program this black box to create, fairly complex set of rules that determine the QoS metrics that you want to have on output traffic. And so that means that threads no longer have to worry about that. That can be essentially factored out of the application logic and put into an overall system configuration. And in order to how that impacts our simplified worker thread, the only real change is that instead of doing a direct QNQ at the end, I now basically hand the packet off to the traffic manager by this new API, ODP TMNQ, which basically takes a handle of a TMQ, which represents the traffic class that this flow belongs to, and hands it the packet, and the traffic manager will basically do the rest. Any questions on that? Yes.
Sorry, I'm newer of this ODP, but as far as I know, the functions you just mentioned about all the traffic management and also QNQ, like the different thread, maybe need to rescaling or synchronization or reorder. Maybe this kind of functions is really like the same function in IEEE 802.1 in Ethernet MAC layer definitions. So I want to know the relationship between ODP and the IEEE 802.1.
Well, are you referring to the priority flow control or which 802.1? Because there's lots of 802.1s.
Yeah, IEEE 802.1 they have many standard specifications like how to retimer, how to synchronize the Ethernet frameworks, and also have the many definitions about this kind of traffic management. So I think the function is really the same. So I mean maybe they can have some relationship between these two different organizations.
Yeah, there's a lot of intersect there. You're right. Again, this is more of an application stuff on output. The 802.1 stuff is most of the specs have to do with input, but they also have to do with how do you handle QoS on the output side, and to that extent, we're doing that. I know, Barry, did you have any comments on that are worth elaborating?
Yeah, I'm not totally sure which parts of 802.1 you're talking about. Like if you're talking about the VLAN aspects and the prioritization and the part of VLAN or the coloring, but typically the way I understand it is that those standards affect the input dropping and prioritization before it goes to the TM. The TM is an egress thing, and its job is much more sophisticated because it's trying to reorder packets and shape packets and do bandwidth management on flows, individual flows, not just overall port flows. So it's working at a much higher level. Plus, it can be hierarchical, so you can have different levels of hierarchy. So I think it's like the way I look at the 802.1 VLAN stuff. It's sort of like the minimum base stuff that feeds into a more sophisticated reordering stuff. But if you want to know more details, you're going to have to point me precisely to the 802.1 parts that you're talking about, okay? And then I can give you a better answer.
So why don't we just stay with the same send API and I mean the queues offered up for the TM versus the packet IO should be transparent to the application. So why do we change the application only when we're using TM and not change it when we're in?
Well, that's a good question. I think the rationale is that TM queues are specifically packet-oriented, whereas queues are event-oriented, and that's sort of the main idea. In theory, I suppose you could have another queue attribute. That this is a TM queue. You could define a queue with a TM queue attribute. This seemed to be a somewhat cleaner way of doing it originally. Barry, I don't know if you had any thoughts on that.
When you talk about the packet I/O queues, there are a fairly small number of packet I/O queues. The queues here in the TM are expected to be much finer granularity, in particular right at a connection level. Like, for example, every TCP connection used by a specific user may have its own TM queue, whereas the egress packet I/O queues, are typically going to be per port, per class. So the orders of magnitude of the queues are very different. In one case, you might have 16 packet IOs times 8 levels of priority, whereas here you might have 4 million TM queues, one for every connection that's going on. So they're much larger, much more fine-grained.
All I'm concerned about is portability, right? So if you have an application that, if you write an application that just goes to the packet I/O and there's a TM, it bypasses it, I guess, but how does an application know there's a TM and when to use a different API?
I don't know the answer to that. That's for later.
Well, these APIs are just being posted to the list now. So if there are comments, now would be a good time to get involved with that. I mean, as I said, the alternative is to Petri.
Yeah, catch it with, even with the jet lag. But anyway, the answer is that the TM side has much more parameters to configure, and there's the whole lot of TM APIs. The enqueue is only one call. There's 10 other calls that you use to configure actually what's happening in the output queuing and shaping and scheduling side and the queue lengths and drop policies and whatever. So there's much more attributes on those TM queues than on input side.
So I think for now that was the sort of the rationale behind that. That's not to say that we couldn't extend things further or provide some other ways of getting at it. But just like when you're talking to the scheduler, that's a change from doing a direct poll. If you are using the traffic manager, which we assume you would want to use. This is just the way of getting the granularity that the traffic manager provides. And again, it's specifically for dealing with packets, because queues in general deal with events, and so they can handle any sort of event. These are specifically for packets. But it does raise the question of, well, how do I migrate applications to use ODP? And so if you look at what a typical application might look like today, and of course we always refer to anything that's making money as a legacy app, so they will typically use SDKs directly or have their own roll your own APIs. They directly tied to some sort of specific hardware platform typically, and they're probably doing I/O via pole node drivers of some sort. To convert that to an ODP app, we view that as occurring in 2 stages. You might have an initial port that uses a mix of ODP and legacy APIs. One of the nice things about ODP is that it's being a framework rather than an environment. You can add it on an incremental basis to existing apps. And to the extent that it's using ODP APIs, well, to that extent, it's retaining some portability, even though it may be limited because it's still using platform APIs. And as a result, we also have some limited set of acceleration capabilities because only the ODP APIs will be accelerated on some other platform. And it's probably doing I/O via the ODP packet I/O poll mode APIs. But once I have the application sort of getting its feet wet with ODP, I can then do maybe a refactoring of that to use all ODP APIs and be fully portable with transparent platform-specific acceleration. It would also be restructured to use the event scheduler for processing and I/O scalability, and probably the traffic manager as well for output. So you can see, moving to an ODP structure for an application in a number of stages. The end result being that you wind up with an application that has all the benefits of using ODP. Any questions on that? All right. Well, I'd like to talk a little bit about the other sessions and demos that you'll be seeing this week. And all of these are really on Thursday. So Thursday is definitely is the networking day. So we've got most of the LNG sessions there. We'll be having a session on core isolation, which is not really ODP specific, but is obviously of great interest to DataPlane applications because it provides the ability to dedicate resources to specific worker threads. We will, yes?
Just a note for people there. The original presenter for that isn't able to make it, so what was going to be a short slides show with him presenting some information is going to be more of a discussion about the topic at this point.
Right. Well, I think we can still present Gary's results. We just may have to take questions back to him if there are detailed questions. It's like, how are you so brilliant to be able to come up with this? We'll have to ask Gary directly. So there's also, we're having an ODP user experience roundtable. So there's a number of people who've now had an opportunity to play with ODP and make use of it, and we'd like to basically share some experiences and lessons learned from all that. And then also Zoltan is, I don't know if he's here. We'll be presenting some very interesting performance results that we've gotten to date on ODP DPDK and its use. Also, of course, on Thursday afternoon, we have Demo Thursday. So we're expecting to see demos from a number of companies, as well as LNG. So that will be something that you'll definitely want to catch. And that's the update for ODP. Any final questions or comments? No? Well, thank you very much for your attendance.